By the second week of August, the bedroom over the garage is sitting in the low 80s at 4 in the afternoon, and the air conditioner holding it there is 9 weeks old. Brand new. Matched coil, clean install, warranty folder still on the kitchen counter. The old unit was 15 years old and everybody agreed it was tired, so the household did the biggest, most visible, most obviously related thing a person can do about a hot room. Central system replacement is the kind of check most families write once or twice in a lifetime, and depending on the house and the equipment, it runs from several $1,000s into the low tens of thousands. And the room that started the whole project came out about 1 degree cooler than it was before. That pattern shows up often enough in home energy work that it barely raises an eyebrow among the people who do it. The install was probably fine. The new compressor probably makes more cold air than the old one ever did. The money went to a real piece of equipment doing real work. It just went to the wrong failure, because in a lot of those houses, the thing that would have actually fixed that bedroom was about 15 feet away above the ceiling in a duct run with a joint that had pulled loose sometime during the previous decade. Cost of that repair: a tub of mastic, a roll of foil tape, and an afternoon. And here is the part that stings a little. That homeowner was not being careless. The 3 options everybody talks about: add attic insulation, seal the ducts, replace the system, get advertised, quoted, and explained as 3 answers to the exact same complaint. Hot upstairs. Every contractor who sells one of them can tell you a true story about it solving a hot upstairs, because every one of them has. So let me get the frame straight before we go anywhere else, because the frame decides everything that follows. These 3 are not 3 competing solutions to one problem. They are 3 different tools that repair 3 different failures, and a hot upstairs is a symptom that can come from any of them. Attic insulation deals with heat arriving through the ceiling. Duct sealing deals with cooling that never makes it to the room. New equipment deals with capacity that was never produced in the first place or was produced in the wrong amount. Buy the wrong one and you have bought a perfectly good tool for a job it does not do. The product works. It was aimed at the wrong failure. The reason people guess wrong is that the complaint is not specific enough to choose with. The upstairs is hot tells you where the discomfort landed. It tells you nothing about where the cooling went. And there is exactly one variable that sorts all 3. Somewhere between the equipment and the room, capacity is being lost. Your entire job, before you spend anything, is to find out where. That sounds like it needs a blower door and a thermal camera and a $400 audit. Sometimes it does. But a short list of cheap observations can usually tell you which part of the house deserves attention first, and they cost nothing but a thermometer and a little patience. Start with the temperature split. Every cooling system running properly in cooling mode drops the air it handles by a predictable amount. Take the air temperature at a return grill, take it again in the supply air coming off the equipment, and subtract. Under ordinary indoor conditions, the split usually lands somewhere between roughly 16 and 22 degrees Fahrenheit. That is a rule of thumb, not a law of physics, and it moves around with humidity. The muggier the air, the more of the machine's work goes into pulling water out instead of dropping temperature, so a split at the low end on a swampy day is normal. Now take a reading at the register in the hot room. If the machine is producing a healthy split and the air arriving upstairs is significantly warmer, the delivery path moves to the top of the list. A leak, a poorly insulated run, low airflow, or a long stretch through a hot attic can all steal capacity before it reaches the room. A bigger compressor does not repair any of those. It only sends more conditioned air into the same questionable route. Second observation: compare the upstairs ceiling with an interior wall on a hot afternoon. A ceiling that feels noticeably warmer is a useful clue that the attic side is contributing. It may be thin insulation, an unsealed penetration, a missing patch over the top plate, or a knee wall detail that the flat ceiling never reveals. If the 2 surfaces feel similar, insulation becomes less obvious as the main culprit, but it does not get cleared on touch alone. Small gaps in moving attic air can cause a large comfort problem without making the whole ceiling feel hot. Third, pay attention to when the room fails. A room that is fine at 9 in the morning, miserable at 5 in the afternoon, and comfortable again late at night is strongly tracking solar and attic heat. If it is still hot at 2 in the morning, delivery and return air problems deserve more attention, but the attic is not automatically innocent. Roof decks, framing, and insulation can release stored heat for hours after sunset, especially when the room has weak airflow. And the free one that people skip: check whether the room only fails with the door shut. Hold on to that list as a set of clues rather than a verdict. Later, one particular house type is going to show exactly why that distinction matters. Duct sealing is the narrowest of the three tools and the one most people underestimate, so it goes first. It repairs one specific failure, conditioned air that the system paid to make and then lost before delivery. Nothing else. It will not lower your sealing temperature and it will not add a ton of capacity. The scale of that one failure is bigger than it sounds. The Federal Energy Star program puts it plainly. In a typical house, about 20 to 30% of the air moving through the duct system is lost to leaks, holes, and poorly connected ducts. Sealing and insulating those ducts can improve heating and cooling efficiency by as much as 20%, and sometimes considerably more than that. 20 to 30% of the air. You are not paying for that air a little bit. You are paying for it fully, running the compressor to condition every cubic foot of it and then venting a chunk of it into a space you do not live in. And leaks are only half of it, because there is a second loss that happens through duct walls that are not leaking at all. A vented attic on a summer afternoon does not stay anywhere near outdoor temperature. Measurements from the Florida Solar Energy Center put peak attic air around 130 degrees Fahrenheit under a shingle roof with poor ventilation, and in their test work, an attic reached nearly 135 degrees on a day when the outdoor peak was about 92. Now run a sheet metal or flex duct carrying 55-degree air through the middle of that. You have a temperature difference of 70 or 80 degrees pushing heat into the airstream over every foot of the run. That same research group ran the comparison that I think should be printed on the inside of every attic hatch in America. Under design conditions, with a peak attic near 130 degrees, they calculated the heat coming down through an insulated ceiling and then the heat picked up by lightly insulated ducts sitting in the same attic. The ducts won. The duct run gained roughly twice what the entire ceiling did. The ceiling is a big, flat, insulated surface. The ducts are a few hundred square feet of thin, poorly insulated tube, but they are handing that heat directly to the air you are about to breathe at the worst possible moment instead of spreading it across the whole room over hours. The household where duct sealing is the right and only answer looks like this. Single system. Ducts in a vented attic or a hot crawl space, a room that comes up short of the others by several degrees, a healthy split at the equipment and a weak one at the far register, and often a whistle or a dust shadow around a boot where air has been escaping for years. Fix the delivery and that room can gain several degrees in an afternoon for a couple $100 in materials. Now the safety line on that stated completely because half-stated attic advice is how people get hurt. Only ducts you can safely reach are homeowner territory. That means an attic with a proper floor or solid framing to step on. You step on framing members or on a plank laid across them, never on the insulation or the drywall between them because that ceiling will not hold you. Attics run brutally hot. Do that work early in the morning, not at 3 in the afternoon, and get out if you feel dizzy or your head starts pounding. If you find live knob and tube wiring, old cloth-wrapped wiring, or anything you cannot identify, stop and call a licensed electrician before you touch or cover anything, and do not use cloth duct tape. Lawrence Berkeley National Laboratory tested duct sealants under real heating and cooling cycles, and the fabric-backed rubber adhesive tapes, the ones actually named duct tape, failed faster than everything else in the test, in some cases within days. Mastic, or a foil tape rated to the UL 181 standard. Anything sealed inside the equipment cabinet at the plenum or on refrigerant lines is professional work. Insulation is the broader tool, and it does something duct sealing never will. It lowers the load itself. Less heat coming in means less cooling needed every hour of every summer, and the same wall of material works in reverse all winter. That is a permanent cut in the load, and it keeps paying whether or not anything else in the house is broken. The trouble is that most houses are quietly nowhere near current recommendations, and depth is deceiving up there. Energy Star's retrofit guidance for an uninsulated attic runs from about an R value of 30 in the hottest southern zone to 49 through the middle of the country to 60 in the colder zones. If your attic already has 3 or 4 inches, the targets shift a little, roughly 25, 38, and 49 respectively for what you add. Now picture what 49 or 60 actually looks like in loose fill, somewhere between 1.5 feet and 2 feet of it. Knee deep. Plenty of houses built before the 1980s are carrying 3 to 6 inches, which is nowhere close, and from the attic hatch 3 inches and 8 inches look almost identical when the whole floor is a gray blanket. And this next piece gets skipped constantly, which is why insulation sometimes disappoints people who did everything else right. Insulation slows heat that is conducting through material. It does almost nothing to stop air that is moving. Air travels straight through fiberglass the way water goes through a screen door. And a house is constantly pushing air upward through the ceiling. Warm air rises, escapes at the top, pulls replacement air in at the bottom, and the whole building becomes a slow chimney. That is the stack effect, and every gap in that ceiling is part of it. The wiring holes, the plumbing chases, the top plates of interior walls, the bath fan housing, the drop soffit above the kitchen cabinets, the attic hatch itself. That is why the official guidance is emphatic about sequence. Air seal the attic plane first, then insulate. Insulation piled over unsealed penetrations buries the problem without fixing it, and if you ever see insulation up there that has gone gray and dirty in a specific spot, that is the material acting as a filter for air that has been streaming through it for years. The safety branches here are firm. Recessed can lights that are not rated for insulation contact need 3 inches of clearance on all sides or a proper rated cover. Insulation packed against a non-rated fixture is a genuine fire risk, so if you cannot confirm the rating stamped inside the housing, leave them alone and get someone qualified to look. Metal flues and chimneys from any fuel-burning appliance need their required clearance maintained with a metal shield, never insulation shoved up against them. And there is one more that people never anticipate. Tightening a house changes how air moves through it, so if the home has any appliance that burns fuel and vents through a flue, a combustion safety check by a qualified technician belongs in the job. If you cannot do all of that, this is a job to hire out, and it is a job worth hiring out. Which brings us to the expensive one, and I want to be fair to it because the cynical version of this conversation treats new equipment as always the sucker's choice. It is not. There are households where replacement is exactly right. A system that is genuinely undersized for the house cannot be sealed or insulated into competence. If the load calculation says the house needs more capacity than the equipment can produce on a design day, more capacity is the answer. A compressor 2 decades old that has lost performance, a unit that has failed and needs a major repair worth a large share of replacement cost, a single-stage machine in a humid climate that cools to set point in 12 minutes and leaves the house sitting damp and clammy. Those are real cases for new equipment, and modern variable capacity systems are meaningfully better at exactly that problem because they can run long and slow at low output instead of blasting and quitting. The specific way replacement fails when it is bought first is worth understanding because the waste is only half of it. The sizing becomes a decision you are stuck with. Proper sizing has a standard behind it. The Residential Building Code points to an ACCA Manual J load calculation to determine what the house actually needs, Manual S to select equipment against that load, and Manual D to design the duct system that will carry it. Manual J counts insulation levels, window area and orientation, air leakage, ceiling height, climate, and room-by-room conditions. Skip it. Size by square footage or by matching whatever was there before, and the near-universal result is oversizing, because installers oversize as insurance against a callback. An oversized air conditioner satisfies the thermostat fast and shuts off. That sounds efficient, and it is the opposite. Cooling equipment removes moisture by keeping air moving across a cold coil long enough for water to condense and drain away, and that takes run time. Department of Energy research on sizing lists it directly. Oversized equipment means reduced efficiency, more wear from cycling, and worse humidity control in summer. So the house gets to 74 degrees and still feels like a locker room. The homeowner drops the thermostat chasing a comfort that is not a temperature problem at all, and the bill climbs. And every one of those consequences is now locked in for 15 years or more. There is a nastier version. If you replace the system before you fix the envelope and the ducts, the load calculation, assuming anyone did one, is measuring the house at its leakiest. You size for a broken house. Then you seal the ducts. 2 summers later, the delivered capacity jumps, and now you are oversized on top of oversized. Time to test the key against real houses, because a diagnostic you never challenge is just a slogan. A 1962 two-story in a cold climate zone. Ducts run through a conditioned basement, never leave the envelope. Attic has about 4 inches of settled fiberglass. Ceiling reads hot in the afternoon. Split is fine at the register upstairs. Room recovers overnight. Duct sealing here is nearly pointless. The air lost through a basement duct leak is lost into the house, where it still does some good. Insulation and attic air sealing wins outright, and it pays in January too. Move to a one-story slab house in a hot, humid southern zone, built in the late 90s. Insulation already at the recommended level, entire duct system in a vented attic. Same complaint, opposite answer. The ceiling is doing its job. The delivery system is running through a 130-degree oven. Sealing and properly insulating that ductwork is the intervention, and adding another foot of blown fiberglass on top of an already adequate attic buys almost nothing. Now the one that breaks the key, and this is the house type you have to watch for. Second story with knee walls. Those short vertical walls, usually 2 or 3 feet tall, that close off the triangular space where the roof meets the floor, most often in a bonus room or a finished attic. In that house, the ceiling can read fine, the split at the register can read fine, and the room is still unbearable. 2 things are going on. The little attic space behind the knee wall is unconditioned and superheated, and the knee wall between it and your bedroom is frequently a bare stud cavity with insulation stuffed in and nothing at all on the backside holding it in place. Building science guidance is specific about this, that insulation needs a continuous rigid air barrier on the attic side, and the floor cavity underneath the knee wall has to be blocked and sealed, or hot attic air simply washes around and under the insulation, and the R value on the label stops meaning anything. On top of that, the ducts serving that room are very often run through that same triangular space. So the key needs a second criterion. When the ceiling checks out and the split checks out and the room still loses, stop measuring surfaces and start asking where the thermal boundary actually is and whether the ductwork is inside it or outside it. Deep insulation lying flat on an attic floor tells you nothing about a vertical wall 12 feet away. There is one more failure the key will not catch, and it costs nothing to rule out. Close the bedroom door with the system running. If the room only misbehaves with the door shut, you have a return air problem. Most houses have 1 or 2 central returns and no return in the bedrooms, so when the door closes, supply air keeps pouring in and has nowhere to go. The room pressurizes. New home programs generally want that pressure difference under about 3 pascals with the door closed, and measured retrofits have found bedrooms sitting at nearly 7 before a return path was added, dropping to under 2 afterward. A pressurized room pushes its own conditioned air out through every crack in the exterior wall and ceiling and pulls hot air in from wherever it can. Transfer grills, jump ducts, or a proper through-door pathway solve it, and the cost is trivial compared to any of the 3 big options. Order stops being a preference right here and starts being money. Do the envelope first. Air seal the attic plane, insulate to the recommendation for your zone, block and seal the knee walls if you have them. Then seal and insulate the accessible ducts and fix the return paths while you are in there. Every one of those steps reduces the load the equipment has to meet. Only then do you let anyone run a load calculation and size a system, because now they are sizing for the house you actually have instead of the house you used to have. It is common for households that go in that sequence to find that the replacement they were quoted a year earlier was a half-ton or a full ton bigger than what they end up needing, which means a cheaper machine that also does a better job with humidity because it runs longer at lower output. Reverse the order and the mistake compounds. Buy the equipment first and you have paid the most, changed the least, and permanently locked your sizing to a condition you are about to improve. So, final assignment. Duct sealing belongs to the household with ducts outside the conditioned envelope and 1 or 2 rooms that consistently underperform the rest. It is the cheapest tool, the most surgical, and pound for pound the highest impact thing most people with attic ductwork can do. Attic insulation and air sealing belong to the household where the ceiling is warm to the touch on a summer afternoon, where the existing depth is well short of the zone recommendation, and where the same work will pay again every winter. It handles heat arriving through the ceiling. Cooling that vanishes in transit stays outside its reach. New equipment belongs to the household whose system has failed, is failing, is genuinely undersized against a real load calculation, or cannot control humidity because it is old and single stage, and it belongs after the other 2 rather than in front of them, with manual J and manual S behind the sizing. The choosing question is not which one is best. It is, where is my cooling being lost? Take the split at the equipment and at the far register. Compare the ceiling with an interior wall on a hot afternoon. Notice when the room fails. Close the door and see if it gets worse. 10 minutes of that will not replace a proper diagnosis, but it can keep the wrong solution from being the first one you buy. Which takes me back to that bedroom over the garage with the 9-week-old air conditioner. That homeowner bought a delivery truck when what they had was a hole in the road. A $5 thermometer would not have completed the repair, but the large temperature loss between the equipment and the room would have pointed the investigation toward the ductwork before anyone replaced the machine. Once the separated joint above the ceiling was found, the tub of mastic finally addressed the complaint that started the whole project. If you go run those checks, I would genuinely like to know what your numbers came back as: the split at the register, the ceiling temperature, whether the door made it worse. Drop them in the comments, because somebody scrolling past with the same hot bedroom is going to recognize their own house in your description, and that is worth more than anything I could add. Give it a like if the checks made sense to you, and if you would rather have the way your house works explained than sold to you, subscribing keeps that coming. Go put your hand on that ceiling.